In this work, we present a 3D design pipeline for generative deformation that automates the procedural perforation of surface models to introduce heterogeneous internal structures that integrate user and simulation-defined control of 3D printed elastic objects. Our main contributions combine generative modeling with automated perforation to introduce a one-to-one pipeline between simulated and printed geometry. This provides an automated generation of elastic structures that can be printed on consumer-level 3D printers with a limited number of elastic materials. The perforation pipeline is defined as a 6-stage process. The input is provided as a surface mesh that is used to create a volumetric mesh with user material constraints. This mesh is then simulated using finite element analysis subject to any applied deformation. The resulting simulation will then parameterize the heterogeneous internal structure of the perforated mesh. The perforated mesh representing the print structure can then be simulated for iterative development. The output of the pipeline is an automatically generated 3D printable hollow surface mesh. In the 2D case, geometric perforation is based on a well-established method for creating geometric insets. For an individual face, the inset is defined by a provided inset value I. This value can be adjusted to change the structural rigidity of the element. For two coplanar faces, we can define two distinct inset values, I and J, that share the same interface. This results in an overlap between insets, forming a 2D edge element made out of 6 distinct nodes. In the 3D case, the homogeneous interface created by inset values that match between coplanar faces is easy to resolve. This is because each node has a corresponding neighbor that meets at the same position. This makes the generation of internal elements required for FEA simulation simple. However, for heterogeneous interfaces, the misalignment between different adjacent inset values creates a more complex internal structure. This forms a 3D edge region that must be filled with solid elements. Based on this construction, there are 3 edge and 6 corner combinations used to fill the internal structure of the perforated mesh with micro-tetrahedral elements. To begin the demonstration of our design software, we consider a simple 3D perforation of 2 tetrahedral elements. Based on a single interface, we can introduce a homogeneous inset value and quickly adjust the structural composition of the object. We can also quickly define a heterogeneous structure by using a gradient between elements with smooth transitions. To apply this process to a provided model, we load the surface mesh, generate internal elements to form a volumetric mesh, and apply a uniform inset. This uniform inset value can then be changed to vary the structural rigidity of the entire object in real time. To define a heterogeneous structure, we can follow the same procedure, but use a falloff tool to define a gradient in the element insets. This provides a smooth interpolation between inset values that can be controlled by selecting different elements. This provides an effective method for controlling localized deformation behaviors. To demonstrate the complete generative deformation pipeline, we provide a time-lapse overview of the design, simulation, and generation of the 3D print geometry created by the geometric perforation. This includes the design of user-provided inset constraints using element selection, the simulation of the expected deformation, and the automated generation of the heterogeneous internal structure. At this point, we can simulate the resulting perforated structure and create a hollow surface mesh of the elastic object. This mesh can then be exported to a standard model format such as OBJ or STL, and then printed on a 3D printer that requires both support structures and has a limited number of flexible print materials. This entire process is incorporated within our design environment. To establish the impact of an object's deformation behavior introduced by the perforation internal structure, we designed 4 test objects and subjected them to a simple twist deformation, each resulting in a very different deformation behavior. To demonstrate the impact that the automatically generated structure has on the elasticity of different objects, we printed various models of different geometric complexity that contain heterogeneous internal structures. By deforming localized regions of these meshes, we demonstrate how this design pipeline can be used to quickly prototype elastic material designs. While multi-material printers provide a wide variety of elastic material compositions, our approach provides a semi-automated solution for creating variable elasticity within existing meshes and surface models using a single material. This enables advanced elastic material designs for consumer-level 3D printers.